into f at x equals a, so some general value. And now we can create this tangent line in Desmos by using some arbitrary a value. So the point, to build a tangent line, we need a point, we need a slope. I have an x value of a, and the y value is going to be whatever you get when you plug a into that function. And a way of writing that to stay as general as possible is just f of a. Now if this was a finite number like 2, you would plug 2 in. 2 squared is 4, minus 1 is 3. But I'm just going to leave it as general as possible and say the y coordinate is just going to be whatever you get when you plug a in. So f of a. The slope of the tangent line is the derivative at that point. So to stay as general as possible, I'm going to say the slope of my tangent line is f prime of a, the derivative at a. So now I can do point slope, y minus y1 equals m times x minus x1. So I've got y minus the y coordinate is equal to the slope of f prime of a times x minus a. So now, pulling this up on Desmos, there's my equation of the line. Y minus f of a equals f prime of a times x minus a. And no matter where I drag this slider now in Desmos, I always have a tangent line at any a value. The nice thing for us, because we stayed generalized, I can now change f of x to be anything I want, like cosine x minus 2x, and now I can still drag this point around and get a tangent. Questions there before we do another example? Let's try a 3D example. Chloe, give me your favorite order triple.
723.
723? Is that what you said?
Yep.
Write an equation of the line passing through, and I'm going to give you 2 points in 3D space. 723, that is a fixed point. But now I also have the coordinate a comma b comma c. Those are just general parameters or constants. So what this is going to look like in Desmos is you'll have one fixed point at 723. And a, b, and c can be any single point. Everything's free. And you're going to draw all of the different lines that are possible with this fixed point and this free point. So let's just first get those points in Desmos. So So I've got 7, 2, 3. It's gonna be out of view, so just zoom out a bit. And now I have the point A, B, C. It's gonna prompt me to add a slider. So now I can drag this around and I realize that A, B, and C can be anything. I'll give you guys a 35-second head start. Write an equation of the line passing through those 2 points. The only thing now is we're just going to stay very general with how we do this.
Yeah, cool.
So to find the direction vector, we can do final minus initial, but you can still just write it as A minus 7. B minus 2, C minus 3. I feel like we've seen enough of these now. We're starting to get really good at this. If we have a point and we have a slope or direction vector, then our x of t is going to be the point plus whatever the direction vector is times t. The y is the point plus the y component of the direction vector times t. So now I'm going to plot this in Desmos. Don't forget to plot parametric things in Desmos. We need, you can write it as an order triple. You can say 7 plus A minus 7t, comma 2 plus B minus 2t, comma 3 plus C minus 3t. And then it's only going to plot a portion of it, so just change t to go from like -10 to 10. So this looks pretty good. I have my line, but again, here's the beautiful thing about this. What happens when I move my slider now? That line moves with it. It's keeping track of whatever the parameter is, whatever I want my slider to be, and it's always going to draw the line between those points. So there's no new math today. It's all the same stuff. We're gonna be doing cross products, dot products, things like that. But we're just gonna have quote unquote parameters or different letters showing up that we can make sliders and Desmos. All right, so I do have a project I'm gonna pass around. The goal is to have Desmos right in front of you as you guys are doing it. This is definitely a group project. So put your heads together, find someone to work with. What was the guess?
The dot product is if they're if the dot product is zero. You could say that two vectors are parallel if they're scalar multiples, or if the cross product is zero.
Same vector or opposite direction. Other vectors.
So if the angle between two parallel vectors is 0 degrees, do you use the dot product or the cross product? Find it.
If the angle between them is zero, then they're parallel.
Right.
That means that the cross product is zero.
Cross product. That sounds really good.
She didn't put the first part of that for the parallel. You guys very well. Yeah, it says the terminal value of A and then back in the parallel. There's two questions here. The
Yeah,
second-
for, and then for orthogonal.
And then the orthogonal one is the 26. Use dot product for orthogonal. And use cross product for parallel.
Or you can write,
Or you can do standard multiple as well.
yeah.
She's pretty simple.
Six fourths, which is 3
Thank you.
4A.
Is that what we got for number one?
Well, the first part, I didn't do the second part
Okay,
yet.
don't worry, I gotta get
You trying not to. Trying not to cheat. Oh. I think I'm gonna take a peek.
Oh, yeah. This is a way that it kind of cleans things up. If you always make the first component one, you're never asking like, what am I multiplying by?
Mm-hmm.
But you can multiply by 8.
Mm. And then using the parallel, finding the parallel line, the final minus initial was like finding the direction vector. When you're saying if they're orthogonal and you do the final minus
To find if they're orthogonal.
initial. Yeah. Because that's what they did, right? Final minus initial, no.
If they're orthogonal, the dot product has to equal 0.
That's right. Okay. Okay. Got it. Sweet. Nope, yep. There you go. It's all of them now. There two vectors.
That's what, I got, but Jay, we have
I mean, yeah, that's it.
Okay. Controls. Oh, this is exactly that. So we got missing J0.
That's like what we did. Or just, you need a point, you need a
Oh,
direction.
this one we can do,
Wait, hang on.
the one we just did together.
Yep.
Controls.
For the next.